Hello guys, my name is Lindsay and I'm a second year PhD student here at UC, Groundwater Hydrology group. This is a work I've been working on for a while now. I started in my master's and continued here, and now it's finished. And I'm going to share it. And we will go with problem description first, and then research objectives. I will continue with methodology, and then we will finish with results. The spatial variability is an intrinsic feature of natural hydrogeological systems. The characteristics of that variability often have a substantial influence on the behavior of the system, and we need to understand the different characteristics present in spatial patterns to be able to understand the system behavior. The accurate modeling of groundwater flow and contaminant transport requires definition of aquifer parameters, transmissivity and storativity, that represent the essential features of the subsurface system. These parameters, essentially transmissivity, vary significantly in space, and their variability has a large influence on the behavior of groundwater flow and contaminant transport. The complexity of the spatial distribution of hydroparameters has led researchers to develop geostatistical techniques. Most models were done based on the multi-Gaussian assumption. In this framework, the main parameters controlling the degree of heterogeneity were the variance of the logarithm of transmissivity and the correlation length. But this model could not describe the full range of connectivity patterns that we find in nature. The complex spatial distribution of transmissivity values leads to spatially connected fast flow channels, along which water and solute fluxes concentrate, causing rapid transport of water and solids in soil, or spatially connected low conductivity barriers along which the flow slows down. Here we see an example, and these are transmissivity fields. They share the same variance and correlation length, but the connectivity structure, as we can see, is very different. So in addition to variance and correlation length, the connectivity structure of the heterogeneity is understood as a property that strongly influences groundwater flow and solute transport. Pumping tests are traditionally used to estimate hydraulic parameters, transmissivity, storativity, and the effect of connectivity on estimated parameters should be understood in order to comprehend the system behavior. So the research objectives are to quantify connectivity and examine the relationship between the estimated parameters and the underlying level of flow permeability, and to analyze the meaning of estimated hydraulic parameters from the pumping test data, and evaluate whether information about connectivity, flow connectivity may be obtained from the estimated parameters. In the methodology, we start with generation of transmissivity fields. We follow the Monte Carlo framework, and we continue simulation of pumping tests and estimation of hydraulic parameters. We also calculate the connectivity indicators, and in the end, we check the numerical investigation of the relationship between the estimated parameters and the flow connectivity metrics. 100 multivariate Gaussian fields were generated using the sequential Gaussian simulation program, and these fields will be referred to as Gaussian fields. And also we know that transmissivity at the location of pumping influences the estimation of flow parameters significantly. So we generated 100 conditional Gaussian fields, where the transmissivity at the one location is fixed. Then, using these generated Gaussian fields with the transformation method proposed by Zinn and Harbin, first the fields with low transmissivity connected channels are generated, and then fields with high transmissivity connected channels are generated. The statistical parameters are maintained the same, but the spatial distribution of transmissivity are changed, and a total of 600 heterogeneous aquifer systems with different levels of connectivity are generated synthetically, and they share all the same systems. Maybe we see it better here. We have unconditional and unconditional realizations, Gaussian and non-Gaussian distributions. For unconditional ones, transmissivity at the pumping location is variable, and for conditional, they are fixed. And the statistical mean variance and integral scale are the same for all of them, total of 600 fields. We see examples of these fields. On the color bar, the red represents the high transmissivity values and the blue represents the low transmissivity values. In Gaussian fields, they are like a mix, but in low transmissivity connected, low T connected fields, low ones, blues are connected, and for the high T ones, reds are connected. Pumping test simulations, they were performed using mode flow simulation model. All synthetically generated transmissivity fields were used in individual simulations. Confined aquifer is assumed, and pumping well is located at the middle of the fields. Pumping is stopped before the boundary conditions affect the test results, and we put 3 observation dots at R over I equals 0.1, 0.5, and 2. R is the distance from the pumping well, and I is in the scale. And for the estimation of hydraulic parameters, we use 3 pumping interpretation methods: Thijs, Cooper-Jacob, and continuous derivation methods. Thijs method uses the full time drawdown curve and is originally the MPT method. Cooper-Jacob is a simplification of Thijs method and uses the late time drawdown curve. And continuous derivation uses both drawdown and drawdown derivative curves to provide estimates that evolve in time. We did the test for the Cooper-Jacob method, with the Cooper-Jacob method too, but the results were very similar to the results of Thijs method. So I excluded them from the presentation to the analysis. For the calculation of the connectivity indicators, we use 2 connectivity indicators: global scale connectivity and local scale. The global scale one considers the whole domain, and the local scale one considers the connectivity between points of interest between pumping and observation locations. The global scale connectivity for each field were calculated using the method proposed by Western et al. 2001. In this method, each cell in the domain is classified as high T or low T based on a threshold value, and a binary matrix is generated. High transmissivity clusters are defined, and then the integral connectivity function used here is defined as the probability of 2 points separated at a distance h fall into the same high T cluster. I will show a small example. This is 15 by 15, and these are transmissivity values for each cell. The threshold is 0 and T is 0. The ones larger than 0 are highlighted with green. Then based on that, the binary matrix is generated. Greens are 1 and the low values are transferred to 0. Then we see the clusters. We have 4 clusters here. We label them. And then connectivity function is the number of connected pairs over number of total pairs for each separation distance. And global connectivity scale is the area under this curve. And using this method, the global connectivity scale of each field is calculated. For the local scale connectivity indicator, this method provides a framework to identify connectivity between 2 points using the concept of hydraulic resistance. The curve connecting the 2 points along which a water particle encounters less resistance is the least resistance curve. The goal is to find the path that minimizes the hydraulic resistance between the two locations, between observation and pumping well. And the method uses Dijkstra's algorithm to find the shortest path. The hydraulic resistance between 2 points, between A and B, is calculated as the summation of 1 over transmissivity A and 1 over transmissivity B times the distance between them. And by calculating the minimum distance from the initial point to every other point in the system, and considering these resistances between points, results part. Global scale connectivity indicator. On average, high T connected fields have the largest global connectivity scales, and the low T ones have the smallest scales. This is even more clear for conditional applications. For local scale connectivity indicator, this time is like the opposite. Low T connected fields have the largest hydraulic resistances, and high T connected fields have the smallest resistances, with large standard deviations. The difference is more clear for conditional realizations because transmissivity at the well location affects the calculation of the local scale indicator. Estimation of transmissivity values using the Tice method. Here we see almost all estimates are close to the geometric mean of the transmissivity, which is 1, regardless of the connectivity structure. But for conditional realizations, where observation values are over I equals 0.1, especially, low fields have smallest transmissivities, and high T connected fields have the largest transmissivities. But the difference is not statistically significant. On the other hand, the estimation of storativity varies a lot. Here we see 3 observation locations at 3 different distances. For the one closest to the well, or pumping well, the variability is higher, especially for unconditional realizations. And the variability decreases as we go away from the pumping location. For conditional realizations, at the closest one to the well, low T connected fields have smaller storativity estimates, like underestimated, and high T's have higher estimates of storativity. Here we compare the global scale connectivity with storativity. The variance again decreases, the variance in the estimates of storativity decreases with distance, and conditional ones are over equal 0.1. We see that low T ones have smaller values than the high T ones. Here we see local scale connectivity versus storativity. We were checking to find a correlation, but we couldn't find a significant correlation, especially for unconditional realizations, because for conditional realizations, again, but for conditional realizations, high-T connected ones have smaller hydraulic resistance, and low-T connected ones have higher hydraulic resistance. We only see that. Now we check the estimation of transmissivity with continuous derivation method. This method considers the diagnostic log too, so the calculations evolve in time. We see 4 or 5 different realizations as an example. At early times, the transmissivity estimate is closer to the transmissivity at the vicinity of the well, but as time progresses, they all converge to the geometric mean again. For storativity, again, it's like the opposite. They start from S0, and then the values vary greatly. And if we go further away from the pumping well, this variability decreases. Estimated storativities with continuous derivation method, but this time we see it as the time evolves. The time increases, and the variability in the storativity estimates increase in time. Then we compared storativity estimates from continuous derivation with connectivity indicators, both global and local scale indicators. And a non-linear correlation is observed between estimated storativity and global scale connectivity, but no significant correlation is observed between storativity and local scale. Here we compare early time transmissivity estimates with late time storativity estimates, and they are positively correlated. So the early estimates of transmissivity in the vicinity of the well has an important impact on the estimated storativity values. Conclusion. The estimates of transmissivity, regardless the interpretation method, are not representative of the actual local transmissivity values in the vicinity of the well point or the observation point, but rather provide an apparent value which is representative of the full aquifer. This has been proved in the 90s before, Chami's work and others' work, but they didn't consider the connectivity, and we added connectivity, but nothing changed. And storativity estimations vary significantly from realization to realization, and this shows that estimated storativities are heavily influenced by the spatial patterns of the transmissivity field and the actual transmissivity values. The estimated storativities show some non-linear correlation with the global scale connectivity. This correlation increases with conditioning of the transmissivity value at the lab, showing that connectivity has an impact on storativity estimation, but not as dominant as the impact of local transmissivity. And lastly, provided that the observation well is at moderate distance from the pumping well, the continuous derivation method can yield estimates of aquifer storativity combined with transmissivity at the vicinity.
Okay.
Thank you.
Thank you. Questions, comments? Yes?
Yeah, I didn't get it when you say that the air divided by the L is smaller than 1. You said that the distance between the observation and the well is smaller than the correlation.
Yes.
But you said that there was no correlation when it's 0 on 0.1. Or 0.5.
Observation locations we are talking about R over I equals 0.1, 0.5.
But you showed before that one figure, the 0.5, and you said that there was no correlation.
We're talking about the correlation of the original Gaussian fields. So you say, for example, the integral scale is whatever, 10 meters, okay, there are no meters here, or 100 meters. And then you put the distance at 0.1, 0.5, or 2 times this distance. Then when you connect the field of the selected field, you keep the same distance. So it was intelligent to say, well, if it's connected, the integral distance doesn't make any sense. Yeah, but it's, you know, it's just to have something to average. Okay, but the integral distance is the original distance of the Gaussian fields, which she generated this space. And then she uses the algorithm of Sinner-Harvey, it's a very funny algorithm, to create well-connected and low-connected fields based on the original Gaussian. And this is the I, what we call it L, but it wasn't very
But you actually have like some distances that are smaller than the integral scale of the.
Yeah, so it's very close. Probably well sometimes
But it's actually always larger than the integral scale in order to get all the conductivities that you have in the field.
Exactly. This which gets go to 30, whatever, 5, 6 down before. 3, 4, one more. One more. Just.
I was talking about the other one.
Which one? Okay, whatever.
So there's the 0.1. There's no correlation there, right? It's like a cloud of points.
Exactly.
So, but I think it's normal if the distance between wells is way smaller than the integral time scale. Of course, there's not going to be that correlation because you are not sampling the entire conductivity values that you actually have. Of course, when it's 2, you sample everything because it's twice the integral time scale. And of course, you have correlation there. But, well, I mean...
You're in what is called non-aerobic conditions. Yes, exactly, precisely. That's one of the results. That the individual organizations are completely different. When R over I is equal to 2, all the organizations are very similar.
Yeah. So that's why there's more correlation.
Yeah, sure. Yes, of course. That's a reason. But I mean, she needed to show when this started. So for 0.1, obviously, you still have noise. For 2, obviously you don't have noise. And for 0.5, you have a little bit of noise. So that's important because we need to know what is the proper R to use in pumping tests, or if it makes any sense. That's the idea. That's exactly. Notice that in most cases, in real life, the pumping tests take place in R over I equal to 0 or less.
Yeah.
Because typically, integral scales are more than 100. Distances of wells when we do a pumping test are close. So, actually, in general, you're in the first case. What you're saying is, but in the first case, it does not converge. Yeah, exactly. That's a result. That in general, in life, the interpretation of pumping test is much more difficult than ICE or Jacob or Continental suggested. I am one of the we suggested a method, but here we say this is only valid if you're really, really far away. And if you are really far away, usually what happens is that you don't see the effect of the pumping. That's a big problem. And that's why she started to work in Turkey. One of the co-workers called Solis in Boğaziçi University in Istanbul. he was the one who suggested, I guess, this was explained to me, I did not, to suggest to study exactly in the features with the continuous derivation method could provide more information on the issue. She didn't show the convergent method because she thought you were going to be too long. You were going so fast that it was 20 something minutes. You could have put the results of the method. I don't want to remove it because there was too much information. No, but you are really fast.
Maybe a few, because I didn't get everything I think. So for instance, your fields that are connected, you don't use Gaussian fields, or you use Gaussian.
It starts with Gaussian. There's a transformation method. The statistical parameters stay the same, but it creates the connected channels.
Yeah. Because the low T, high T, so the average mean, let's say, the is to the same.
No.
And another question, it's only you.
And the variance, the mean and the variance. Yes.
And when they are low and high T, so you connect the low T's or the high T's?
Yes.
And there's a sort of.
You mentioned the blocking is difficult to see, but once you see it is nice. Huh?
Yeah, it's
Low T, low transmissivity.
You see that you can follow rules.
better connected than the.
In the one on the left, to go from red to red, you have to jump. In the one on the right, to go from blue to blue, you have to jump.
Okay.
And in the one above, you have to jump always.
Yeah.
Which is the opposite. So they look very similar, but if you're careful, they will be different.
Because you also talk about storativity, that's a storage coefficient. That's constant, or because then you do a sort of. I think you do it with the phase of the when you estimate the storage coefficient from the
Yeah.
This is the convergent. This is the one she did not show, but but you get the same results.
So you just look at
This is convergent, yes, late part is convergent.
range and
But this is the one which didn't show, but there's also the same. And there are three methods. One of them is to say, which is the one we explained in class. Then you have with the full curve, which is the nice. This is the one that Custodio explained in class. When we were in Custodio's classes, it was slow. And the continuous derivation method is the one that is not yet started in class, which is a pity because it's the best one, of course. And it provides many results, not one. It's much of time. Well, gives you more information because you see the result.
Because you cannot look at all the 100 or 1,000, you don't do it by looking at each individual one. Yes, so that would be better.
Yes.
Yes.
Try it.
That was one of that was a different job, I guess, making all the algorithms to interpret the 600 tests to the
I don't know whether there are people in the chat wants to say something. Okay, people from the online audience, you can also say something. Okay, or put something in the chat. No comments from. Okay.
Okay.
All right.